Hello, welcome back. In this segment we're going to talk about pointers and arrays. So we're revisiting arrays with what we know now about pointers, and we're going to discuss the relationship between pointers and arrays. You really need a piece of paper and a pencil. We're going to draw pictures as we go along with this. It's not that hard conceptually. Let's just start. So here is a declaration of a simple array of 5 double values initialized to these values. And here's the picture that we've been using up until now of how we look at an array. And we've always had this arrow here as if it were meaningful but unexplained. So let's start out by saying that the name of an array, in this case the variable name data, it actually contains something. And what it contains is the address or the pointer to the first element in the array. So you can try this. Print out the name of the array using a %p, and you'll see that it's an address, and it is the address of the first element in the array. The data type of the name of the array is a pointer to the first element. So the elements in a double array are doubles, and that means that the name of the array is a double pointer, a pointer to the 0th element. What we can observe now is that what's pointed to by the name of the array is the 0th element in the array. So this relationship is always true, and you can always think of it as what's stored in the name of the array is the address of the 0th element. So this equality is also always true of arrays in C. So what is the significance of this, that the name of the array has an address in it, and it's the address of the 0th element? Well, let's look at the picture first. When we start talking about using the name of an array as the address, it's easier to make up a number. Suppose this array fell at address hex 1000. It won't. I just made that number up. What are the addresses of the other elements of the array? Well, a double takes up 8 bytes of space. So data sub 1 is at address 1008, and data sub 2 is at address 1010. These are hex values, so add 8 to 8 and you get 16, which in hex is 10. Add 8 to that and you have the address 18. So each of the elements in the array has an address, starting with the address of the 0th one, which is stored in the name of the array. When you declare an array in C, you're guaranteed that they are contiguous in memory. So we don't decide to store the first few elements in one part of the RAM and then the remaining elements someplace else. You're guaranteed when space for an array is allocated that that is one chunk of memory, and you can rely on these being exactly 8 bytes apart. Okay, let's revisit passing an array to a function. So here's the option that we used previously, and we're going to call this the subscript syntax. So when we declared a function where a parameter was an array, we have these square brackets, and that means that what gets passed into this function as the first parameter is going to be the name of an array. So here's a call to pass an array down here. Pass the name of the array, and it matches this parameter data type. Now that we know that the name of an array is a pointer, we can use a different syntax, and we can say when we pass an array, what we're passing is a double pointer. So this new syntax, this new option, would work with the exact same call here. What are we passing to the function? We're passing the name of an array, and the name of the array is a pointer to the first element. It's only one number. So this also should explain to you why we have to pass the size of the array along with it. So when we call this function pass an array, we're passing only 2 numbers, the address of the first element and how many elements there are in the array. There's no way that the function could know how many elements there are in the array just by having the starting point. So we have to pass two values when we pass an array. Okay, now let's look at a picture, and this is the place where you might need a pencil to help you understand this. We're going to use the new pointer offset syntax to look at passing an array to a function. Okay, here's the picture of the data over here on the right, and we're going to say that this array falls at location hex 1000. It won't, it's an easy address to work with. And let's fill in the addresses of each of the elements in the array. And what gets passed here when we pass the array to the function is the address of the array, or the address of the 0th element in the array to be more exact. So in fact the number hex 1000 in this example would get passed into here. So the variable array in the function holds the address 1000. And the other value that's passed is the number 5 gets passed in here as the size of the array. Okay, now let's work in here inside of the function where it's been passed as an address, and we're going to write a loop that will print out the array values. So this should be familiar to you, a loop that goes 5 times. And now this is the new part. We're going to print out what's pointed at by array. Well, what value is in array the first time through this loop? It has 1000. What's pointed at by 1000 is 1.5. Now, this is new, adding 1 to an address. When we add 1 to an address, we don't actually add 1, we add as many as it would require to move to the next element of the array. So C knows that because the data type of array is a double pointer, when you add 1 to a double pointer, you actually add 8. And that moves you, because there are 8 bytes in a double, that moves you to the next element in the array. So the second time through this loop, when we print out what's pointed to by array, we're going to print out 2.6 and add 1 to array using pointer arithmetic. It moves us along the elements of the array, and we can achieve what we had achieved before using the subscript syntax using pointer or pointer offset syntax. Well, there are more ways of manipulating arrays using this syntax. This one is a slightly simpler example. It takes one less line of code. We have the same objective. We're going to pass an array to a function, and then we're going to print out the values in that array. Now, as I increments, array plus I will get larger. So remember that array is the address of the 0th element, and if we add I to it, we would have the address of the ith element. And now the dereference operator says what's pointed at by array plus I will be the ith element in the array. So this is the same as array sub I using the subscript syntax, but we have the pointer offset syntax. Here's a slightly different way of doing it. We can make a for loop using, instead of a control variable that's an int, we can use a control variable that is a pointer. So what's in P? It starts out as the address of the 0th element, and it continues for as long as P is less than the address of the last element, and increment P. So this is the pointer arithmetic. In this example, we increment the pointer as part of the for loop, and then inside the loop we can print out what's pointed at by P. If you're wondering why we have all of these different ways of achieving the same thing, we don't really need to. It's just important that you understand that there are a lot of ways of manipulating array elements other than the square brackets, and understanding what's going on in the array in terms of pointers is going to be quite important in the upcoming segments. So let's go into the development environment and look at the code examples that we showed here. Okay, here we are in the development environment, and I've taken that code from the slides. Here is the declaration of a double array that has 5 elements, and we're going to call the function pass an array, and I want us to look at what's going on in the debugger. So let's run to that breakpoint. Okay, we've run to the breakpoint, and the first thing to notice is that data, the identifier data, has an address in it. It ends in 12FF3C, and when we pop that open, we can see the elements of the array, and in the main, the compiler and the debugger knows how many elements there are because it was declared right here. We're going to step into this function passing in the value ff3c and 5. So I'm going to step in using F11, and here we are in the function, and this identifier array has in it the address that we passed in. This is the address of the 0th element in the array, and we've passed in the value 5, which is the size of the array. When I try and pop this open now, the debugger can see what's pointed at by the name of the array, but it can't tell how many elements there are, so it doesn't bother to show you a million of them. It doesn't even try to guess that it's looking at an array. It only knows that this variable array is pointing at a double. Okay, so as we go through this loop, what's pointed at by array, ff3c is the first element of the array, and we can print out that, and then add 1 to the address. ff3c plus 1 is ff44. Okay, if your hex arithmetic is not that good, we can go into the calculator and say in hex ff44 minus ff3c, and we see that the difference is 8. So adding 1 to a double pointer actually adds 8 to the address, and you can confirm that. Well, you can see everything that's happening. So as we add 1 to the pointer each time and print out what's pointed at by that pointer, we're looping through the array elements and printing out the contents of the array. We can go out to the application that's running and see what its current progress is. So I'll step through this a little bit more. You can see the pointer increasing, and what it points at is now junk, so we must have finished, and we did. It's a little bit tricky to make sure that you don't step past the end of the array, and if you do in C, for example, as this pointer was incremented the last time, you can see that now we're pointing at a piece of data that's not part of the array. It's what comes after the array in RAM. If you do something to that piece of memory, then you have the off by 1 bug where you stepped past the end of the array by 1. Okay, I'll just let this finish, and we're going to look at the other examples that came from the slides. I've just copied them in here, and I called them B and C. So we have the same objective each time. We're going to print out the values in an array using various techniques for using pointer and offset syntax. So each of the 3 function calls is identical, but the code, the loop, it demonstrates 3 different ways of manipulating an array. So I'm going to step into this one. This is the second example from the slide, and this is the one that best demonstrates pointer offset syntax. So array holds the address of the array, or the address of the 0th element of the array more correctly. And if we add I to it and then go to that address, we will have done the same thing as using the square brackets, the subscript syntax, and we have array sub I here. So this for loop is the same as we had in subscript syntax, and we use the dereference operator and go to the address of the ith element. And if we step through this so that you'll believe it works, there is no addresses changing this time. This is a temporary. Each time through the loop we add I to the original pointer and then go to that address to print out the value in the array. We can go out to the application and make sure that it's doing what we expect. Okay, let's look at the last example now. I'll step into this one, and in the third example, this one is the one that causes people the most grief, I think. We're going to use a pointer in a for loop as the control variable in the for loop. So the initializer says, let this double pointer p point at the 0th element of the array. That's the number that was actually passed in here, the address of the array. And then we're going to continue while it's less than the address of the last one, and increment the pointer. And remember, that's adding 8 each time through, and what is pointed at by p will be, we can pop it open in the debugger, one of the elements of the array. So the first time through, where p is initialized to the address of the 0th element, what's pointed at by p is the value in the 0th element. I hope you took the advice of a pencil and paper and drawing pictures, because it's not easy to manipulate data using pointer arithmetic. There's nothing hidden from you, and it's only numbers, but it's more abstract than what we've been used to. So you can see this in this one, we are looping through the elements of the array in the third and final way that's demonstrated in the slides. So you might want to go back and forth. You might want to type in this code and make sure that you're understanding what's going on in these 3 ways of manipulating an array using pointer and offset syntax. Okay, before we leave these slides, I would like to just point out one pitfall of using pointer arithmetic. Sometimes you would be wanting to add 1 to a pointer, and sometimes you want to add 1 to what's pointed at by a pointer. Those are different things. The increment operator. This example is a post-increment operator that grabs onto what's on its left. So this increment operator grabs onto pi, which is what data type? It's an int pointer. The second example, with the parentheses, grabs onto what's on its left, what's pointed at by pi, and its data type is an int. There are cases where you would want to do either, and you have to make sure that you're grabbing onto what you want to add 1 to. So the first one is pointer arithmetic, where you're adding 1 to an address, and the second one is where you're adding 1 to an int. You can also use a pre-increment on these to kind of avoid the parentheses if you want to. I don't much like this. I think it looks odd to use a pre-increment and grab onto what's pointed at by pi. So this would be an int arithmetic, not a pointer arithmetic. There is no way to add 1 to the address if you're also dereferencing it in the same statement. So this one is very uncommon, but both of these are in common use. So that's the end of this segment. I hope that you're understanding pointers and pointer arithmetic and using arrays to have a better understanding of how pointers work is kind of a good thing to do. We're going to be using these pointer values in the rest of this course. I'll see you in the next segment.